Thank you very much for the invitation. And I would like to thank the organizers, Bhabani and all the other organizers. And needless to say, I would also rather like to be there in the institute in Bangalore than sitting here at home. Yeah. So my talk, the title has changed a little bit. I had also in the title something about how gauge equivalence works in this context, but this was too long. I cut this out. So my talk is based on joint work with my former student, Julia Sen, Francisco Coher, and also Takanobu Taira, who is one of my current PhD students. And it's a number of works I want to discuss, all sort of based around solitonic kind of systems. And I want to give a rough flavor about the results of these works. So first question is, of course, why study complex PT systems in the first place? Just the motivation. Well, we are really interested in, do they still have real energies and therefore might potentially be interesting physical systems? So, and at the same time, we can also solve a lot of interesting outstanding problems which couldn't be solved before, namely a degeneracy problem. I will say what I mean by this. And there are also new features we can discover. I will also comment on some of these. And one of the new features is what we refer to as non-locality, and this is introduced while what is usually referred to as the curvature condition. I want to comment a little bit on the technicalities and how this non-locality is then reflected in solution procedures. And there's a number of solution procedures for solitonic systems. There's the Hirota method, there's the Darboux method, there's inverse scattering, etc. And I will show how this comes up and is implemented in Hirota's method and in Darboux's method. And then a different type of equations, which are sort of more simple version of solitons, I'm using here solitons in a rather loose sense, are BPS equations. And they usually come up in gauge theories originally, where these equations can be arrived by some multi-scaling limit, which is motivated on physical grounds. And in particular, you can identify magnetic monopoles. And Takanobu Taira will talk about this also in this conference. And since I'm talking here mainly about 1+1 dimensional theories, I will focus in this talk on BPS systems related to 1+1 dimensions. But you can also extend this to 3+1 dimensions. And in particular, there's an interesting model, which is the SCRUM model, which is supposed to mimic quantum chromodynamics. And Francisco Coher will talk about it. And then I will have some general conclusions as well. So what kind of systems are we looking at? So here is a sort of prototype integrable system, which is the KdV equation. So that's one of many examples one can look at. And if we just, you can make this complex and PT symmetric, you can deform it. There are all kinds of manipulations you can do to this equation to get a non-Hermitian system, which is still PT symmetric. So here I just use a very simple way to make it complex. Namely, I just take U, the field, to be complex rather than real. And if you look at the real and imaginary part, you can also look at this equation as a system of coupled equations. And they are not entirely unknown. In some special cases, they're reduced to some known integrable systems. So if I simplify this term over here and leave out one of the derivatives, I leave out the term pxq, then it becomes the Hirota-Satsuma equation. And if I set the third order derivative here of q to 0, then it's reducing to what is called the Ito system. And all these systems, this general system, have, of course, in common that it is PT symmetric. And so here's the PT symmetry, also written down for the components P and Q. And crucially, for this system, this isn't always true. If you deform it, this is no longer true. But in this system, we can make use of the fact that it's integrable. So here we can write down an explicit Lex pair. And once you have a Lex pair, it's established that your system is integrable. Now, how to solve these equations? There's one method, and I'll just give a flavor of this. It's called the Hirota bilinear method. And you convert the system into a bilinear form. That's the trick here. I will not have time to go in more details on this. And once you have it in this form, you can systematically solve this system for what people often refer to as a tau function, which initially is an expansion. It looks like an approximate solution, but the series actually terminates. And if you make this kind of ansatz or Ansätze for the one-soliton solution, this would be a one-soliton solution, this is a two-soliton solution, etc. The series terminates, and your formal parameter lambda in the end can be set to 1, and you have an exact solution. That's how you can roughly, well, I didn't say how, but you can solve this system exactly and get all your N-Soliton solutions. So here's a one-soliton solution. It has, of course, now a real and an imaginary part. And surprisingly, when you set our generic parameter theta to plus minus pi over 2, we recover a solution which was previously obtained by Kara and Sashena. They have done it in a very different way. They assumed that your solution will be sort of an hyperbolic form. They make a generic ansatz, and they find or found this particular one-soliton solution, which is a special case of our generic solution over here. And that's how it looks. That's the real part. It looks very similar to a standard soliton, but it has here these little tails, and it has a little additional structure. And the imaginary part is an odd function which looks like this. So this is the one-soliton, and the question is also now, when are your charges real in this context? So the mass, momentum, and in particular the energy, we want to know, are they real, and why are they real? And can we generalize this to other scenarios? So if here's a simple argument, when we implement the PT symmetry I wrote down before, then it's a one-line argument to show, without any calculation, that your energy must be real. That's a very simple argument. But now we can break the PT symmetry, and this parameter mu I had here before. This is this shift parameter, if I can still find it. No, I don't. I didn't, in fact, write it down. But if we shift now our solution by kappa plus I, here actually it's defined. So this parameter is shifted. And then I have broken the PT symmetry. You see here now the argument is just x plus a constant. And if I set x to minus x, I cannot compensate this now with the kappa over alpha. But since I have here an integral in x, I can just absorb this kappa over alpha into the limits, and then I'm back to my PT solution, and I can use the argument in the previous line. Now, I could also shift in t and use the fact that these are charges and therefore conserved in time, and therefore it has to hold for all time, and I can shift in time. But now I have used up my two variables. So what about N-Soliton solutions? And since this alpha parameter here refers to the speed, I will get different types of shifts, and we will no longer be able to absorb these quantities in the limits, or using the fact that we have conserved charges. So we need some other arguments. So this puzzled us. Why are the solutions real, despite the fact that PT symmetry is broken? That's the question here. And to answer this, we need to understand a bit more how N-Solitons behave and what are the sort of key properties of solitonic solutions. So here's a two-soliton solution obtained, as I explained, well, not explained, as I indicated, from the Hirota's bilinear method. And you have the typical behavior. There are two solitons, one faster than the other. They scatter, one overtaking the other. And a similar behavior we can also observe now for the imaginary part. This is a complex soliton, not to forget. And we have this kind of scattering. And after the scattering, the soliton regains its shape. That's the key definition, in fact, of a soliton. But this is not all what happens. What really happens is there's a little shift. As you can see here, the red curve is a two-soliton solution, and it's compared to two one-solitons related to the speeds alpha and beta, which are inside the two-soliton solutions. And you can see here, once they scatter, the two-soliton of the two-soliton solutions, there will be either a little delay or a little advance of one of the components. And you can compare this by looking at the one-soliton solutions as a gauge. And the same happens if you look at the imaginary part. So the question is now, can we calculate these shifts, either in time or in space? And the way to do it is you compare your solutions in the asymptotic past and the asymptotic future. And you can indeed, when you do this for the two-soliton solutions, compare with the one-soliton solutions, you find that the shift in either in time or in space, depending on which variable you want to pick at, is calculable, and it's this closed expression over here. You can calculate this analytically. And the same happens for the imaginary part as well. There's a similar shift. It's the same. I mean, they run in parallel, and you will calculate the same time delay or the same displacement. What about three solitons? Now I compare a three-soliton solution with three one-soliton solutions. And now we have different types of shifts. The particle with speed alpha can scatter with the particle of speed beta. It can scatter with the particle of speed gamma, and also beta can scatter with gamma. And the same happens also for the imaginary part. The shifts will be just the same. And here are the solutions. And you see here the shift in the alpha compared to the overall movement is the sum of the two shifts in beta. And in beta, we have a difference in the shifts of two particle scattering, and also in the gamma, we have two negative ones. This is the outline, or the time delays. This is just translated to time here. So the N-Soliton time delays is the sum of the two-soliton time delays. That's the result here. And in fact, that's what we know very well from the quantum field theory context. That's in fact the notion of integrability in quantum field theory, that the S matrix factorizes into two-particle scattering S matrices. And the underlying equation in this context is the Young-Baxter equation. If you have backscattering, if there's no backscattering, then it's referred to as the bootstrap equation. Where you use the factorization property on a fusing process. And this is the classical analog to this. So everything reduces to two-particle scatterings. So now we use the fact that asymptotically, the complex N-Soliton factorizes into N1-solitons. That's what we just observed, and we know precisely how this happens, namely there will be shifts. Yeah. And that means we can refer back to our original argument on PT symmetry. Yeah? So the reality of the one soliton can be guaranteed by PT symmetry, the reality of a two-soliton as well. When I use these little shifts, I can always reintroduce a PT symmetric solution. But when we had an N-Soliton, we couldn't use this because there weren't enough variables to shift with. But the fact that our system is integrable allows us to go back to the one-soliton solution. And so I can conclude here, integrability plus PT symmetry will ensure the reality of all charges for all N-Soliton solutions. So to another problem, so we know these solutions are real. There's an issue also. What about, and there's some physical motivations to look at this. I will not have time to go into this. What about degenerate solutions? So these parameters alpha and beta, they're related to the speed of the soliton. But whenever you just naively send alpha equal to beta, your solution will become infinite. You can't take this limit. This is a non-trivial limit. In the best case scenario, we can create cusps. Yeah. But in the complex case, these limits can be calculated. And we can do this in various forms. We can implement this in the Wronskian for calculating tau functions, or also directly in Hirota's method. So I will not explain that. That's too technical, but I will show you what comes out when we perform this limit. Yeah. So the message from this slide is simply it can be done. Yeah. But it's very technical. So here's a solution where this has been done. Yeah. We have carried out the limit, and this is now, here it is. It's a two-soliton solution where we carried out the limit of beta going to alpha, which can be done in a complex model. And you can see here, it's really degenerate. They're moving at the same speed. They just exchange position at the origin, but they move simultaneously. And similarly, also the imaginary part has this property. You can see the two soliton, one soliton structures, how they overtake each other. But this is not entirely true. In fact, if you look at very, very large time, so this is true in a very, very large regime around the origin, you will not see any of the solitons moving faster than the other one. But if you would go out very, very far asymptotically, you would see a difference. So they're approximately moving at the same speed, but not entirely. And the reason is there are these linear terms in T. So there are two types of dispersion relations here. And the linear one here, that relation will make the particles move differently at large time. So same question as before, can we calculate the delays? And we can. Again, same approach. We look at the asymptotics. And then we find now for this degenerate model that the relative displacement depends now on time itself. So it's no longer time dependent, but we can still calculate this. And the same happens for the imaginary part. It just moves in parallel to this. So we even managed to do this for an n-particle solution. This is a long calculation, but we found a closed expression for the time delays, in this case for an N-Soliton solution, looking at the asymptotics. Yeah, so this is the closed expression here for a degenerate N-Soliton solution. Let's look at another system, and I just want to discuss another concept now, namely non-locality. Yeah, so I explained now why solutions are real, how this works, and that one needs integrability plus PT symmetry, but one can actually get new types of solutions as well. And this is what I want to explain now in the context of higher order nonlinear Schrödinger equations. So here's the nonlinear Schrödinger equation, and I will add now a higher order term to this. And you can think of this as, in a way, as a PT deformation, because this term here, you see here, has an I in front, and all these, the I pick up from, the minus sign I pick up from the PT symmetry, which changes I to minus I, is compensated here by these odd derivatives. Yeah. So this is a higher order nonlinear equation, nonlinear Schrödinger equation, and it's known. So when epsilon is 0, we recover the Schrödinger equation, and when the constants here are in particular ratios, we get a set of known integrable systems. And the system I want to look at, or we want to look at here, is when we take alpha, the alpha beta gamma ratio to be 160, then we get what is known as the Hirota equation. So that's the equation we want to study here. So that's a known equation. So what is new? Well, you know that this equation is integrable from the zero curvature condition. Yeah, once you have a zero curvature condition, you can construct infinitely many charges, and that's the feature here of classical integrability. Now here's the formulation for the Hirota equation in terms of the zero curvature condition. All these quantities are known. Yeah? And once you work out the zero curvature condition, you get two equations. These two equations over here in red are the equations which come out of this zero curvature condition. Yeah, so this zero curvature condition holds up to these equations. And what one normally does is, to make this compatible, one chooses R to be Q conjugate in this context. With a kappa in front, it doesn't really matter. You can just set it to 1, but there's a freedom to have a kappa. And when you do this, the two equations just become compatible, and then you get the Hirota equation. Yeah? So this is the known procedure. But realizing that the system is PT symmetric, we can have other choices. We can take R to be kappa Q conjugate, but now the X has been changed to minus X, and we keep T to be T. And we have also to manipulate slightly the constants. Yeah, we have to set one of the constants now purely imaginary. But if we do this, now the system's one equation becomes just the P conjugate pair of the other equation, and they are also therefore compatible. Yeah. So we have a new type of equation, and that's what we call non-local, sorry, because we have fields, they depend on X, and we have some fields, they depend on minus X. Yeah? And the notation used here is using just the standard letter for quantities depending on X, and I put a tilde on top when there's a minus X. So this is a new type of equation we can look at, and by construction is also integrable because it came from the zero curvature condition. And of course, there are more possibilities. I can take the T to be minus. I can also mix this up and take X and T to be minus. That's really the PT conjugate pair. I could keep one of them real. Yeah, I don't have to conjugate them. And I can either change X to minus or T to minus. So there are different types of equations coming out of this principle just utilizing the PT symmetry, and they have all different properties. They are not equivalent to each other or easily transformed. They are equations having different types of properties. And we can solve them, once again, using Hirota's method, but there's some difference now appearing. So usually we get these, so the equations we have to solve are these Hirota bilinear equations. I explained this briefly before for the KdV system. In this case, the Hirota equation has two equations to solve. But the principle is the same. You expand them, and the solutions become exact because the series terminates at some order. Now, when we have the non-local scenario, we get another equation. Because this equation here we get by just comparing is not yet bilinear, but we need to impose another equation so that it is becoming bilinear, and we can factor out one of the terms. You see here the blue equation has 3 factors, and one factor has to go. So we have an additional auxiliary equation to solve. That's the key message here, but it can be done. So here's the solution. We make our usual ansatz for the series, but now in addition we need to make an ansatz for the H, and we get this set of equations, 3 equations, and we solve them order by order and have 6 equations to solve, and subsequently we can just set epsilon to 0, and that will give us, in this case, a one-soliton solution. To go to higher order, we have to extend our ansatz for F, G, and H. Now, what puzzled us is that we have a huge zoo here of solutions for all these extensions, etc. But for the Schrödinger equation, nonlinear Schrödinger equation, the non-local principle for one of the options was already used before, but our solutions did not correspond to the solutions found by those authors, by Ablowitz and Muslimani. It was different. So we were puzzled why our solutions did not reduce to the nonlinear Schrödinger equation solution in the non-local case. And the reason is the following. There are more options now here as well. We can solve, so here I solved 6 equations, or for each order I solved this equation. But we could set, and subsequently I set epsilon to 1, we could change the order and set in some of the equations epsilon already to 1, solve the equation, and then in the end we set all the other epsilons to 1. So doing this for the last equation and solving then only 5 equations will give us a new solution. And that's the solution found previously. And you can see here from the plots, they behave quite differently. So this solution has, it collapses eventually. And this one is more periodic solution. So there are different types of solutions coming out of this scheme now, because we have more options which you would not have found before. And we can do this also for two-solitons. I will not discuss this, and you get, again, different types of solutions. So there's a huge zoo of new solutions one can discover. How am I doing with time? Can I just ask? Geraldine, how am I doing with time? How much time do I have?
Sorry, I was muted. So if that's okay, 5 minutes, so that we have a few minutes for questions. Okay,
thank you. So the reason I'm asking, then I will not explain this now in detail. You can also implement this in another solution procedure, which is the using Darboux-Krum transformation, making use of the fact that you can have some supersymmetric analog in quantum mechanics represented by some intertwining relations, and you can keep going and iterate these intertwining relations. And as Joshua indicated in the question to Fabio, the interesting thing is here that the solutions you have then correspond to some potentials here. Yeah. So you generate new potentials, but in the context of when we translate it now to our soliton equations, these will be N-Soliton solutions. Yeah. So in this case, for the system we are looking at, we can write this Hamiltonian in a kind of Dirac form. We can iterate this. And so here in red, this is the comment I made about the correspondence between multi-soliton solutions and iterated potentials. And the technical point is here, again, we have more options, and we can implement in what is called the seed function. We can implement the non-locality, and it's then inherited in the solution procedure. Yeah, so you can implement this nicely. You can implement it for the N-Soliton solutions. And it's all coming down to the initial seed condition. Yeah? And then you find new solutions. So the last topic I want to talk about is BPS solitons. So BPS stands for Bogomolny-Prasad-Sommerfield. And these equations come out originally in the context, from the context of looking at non-abelian gauge theories. In there, you also have a set of equations you want to solve, your equations of motions. You want to find the classical solutions. And they are very complicated, and you can't really solve them. But with this clever multi-scaling limit, taking some of the masses to be very small compared to others, yeah, you can set up a multi-scale limit, setting some terms to 0, keeping some ratios constant. That's the key here. You get a system you can solve. Yeah? And Takanobu Taira will talk about this in this context of non-Hermitian theories, how you get out magnetic monopole solutions in non-Hermitian systems, which have still real energies. Now, in general, you can forget about these limits, and you can think of some properties these theories have once you have taken the limit. And you can just study BPS theories in their own right. And that's what we have also done here for, presented for 1 + 1 dimensional theories, but you can also do it for 3 + 1 dimensional theories. The trick is to complete the square here of the energy and assume the red equation that these quantities, they can depend on the scalar field, on the derivatives. Yeah, this is just a shorthand notation for a whole bunch of terms, but they have to satisfy these Bogomolny equation. And the key is that once you're at this limit, yeah, you're satisfying the Bogomolny bound, because in general, higher dimensional soliton solutions, they are unstable. They're not stable, unstable. They are because of Derrick's theorem. But once we are at the bound, there's a chance that they are physical because they cannot go any further. We are already at the minimum. Yeah. Now you can set this up, this system. You define your energy and your topological charge in this way, and then as a compatibility requirement, you get the Bogomolny equation. Yeah. Bogomolny did it the other way around. He completed here the square, assumes this, and then you get the topological charge. And at the bound, E is equal to Q. And here's an example of a non-Hermitian coupled sine-Gordon system. Yeah? So you get two equations out of this, two equations of motion, one corresponding to the self-dual solution, one to the anti-self-dual solution. And they admit now what we refer to as a modified CPT symmetry. So modified because...
You have 2 minutes left, sorry.
Okay, thank you. Because it's not standard CPT. Yeah? There are signs appearing all over the places, and there can even be shifts. Yeah? So it's a different type of CPT symmetry, but this symmetry guarantees the reality of the energy. Yeah? And what initially confused us a lot is that the symmetry here mixes up different sets of equations. You see here, the self-dual equation goes to the conjugate of the anti-self-dual equations. But the energies are degenerate, and that's key here, of the fields respecting the symmetry, and that will again guarantee the reality of our solutions, despite the fact that they are complex. Now we can, of course, then calculate this. We calculate the limits. In the Hermitian case, when lambda is 0, we can do this all analytically, and this is the energy we get out. In the non-Hermitian case, when lambda is not equal to 0, we can do it still numerically, but asymptotically, the limits are the same as in the Hermitian case, and therefore the energies will be the same as in the Hermitian case. So finally, we can analyze which vacua are interpolated, so we can identify the vacua of the model, and we can nicely see, I speed up a little bit because of time. Here, the vacua, just explain the plot a bit. We have here the vacua, and then we can show that a particular solution will always interpolate certain types of vacua in this model. So I conclude. So a general conclusion is if you have complex soliton solutions, then they can be guaranteed to have real energies once they satisfy certain properties. It doesn't always work. For some deformed cases, it does not work. But the examples I showed you work, and there are plenty of examples one can find. One can find new types of behavior. One of the behaviors is that you can introduce non-locality. And the other type of new behavior is that we can carry out degenerate limits, and we can study solutions of these type of systems. And then I showed you a little bit how this is implemented in the solution procedures. And the second point here, second last point I did not discuss. This is the part I skipped. And the interesting bit is that you can also have BPS soliton solutions, and we can have them in 3+1 dimensions. This is another talk by Francisco. And we can also see how this is implemented to get magnetic monopole solutions, which have real energies, despite the fact they're related to non-Hermitian theories. So thank you very much. I will stop here.
Thank you very much, Andreas. So do we have questions, or do you have questions, the audience?
Yes,
One or two short questions. Yes, please.
Hi, Andreas. This is a very interesting talk. Thank you. Just one brief question, and if possible, I have some other questions. But if you can linger after the last talk, so we can take advantage of the Zoom and discuss. But the concrete question I want to ask right now is, in your argument for the complex KDV multi solutions, you used the factorization of the S matrix, or the classical analog thereof, and the reality for single soliton, the charges, the energy, the momentum, etc. The argument from the single soliton. But your argument was for the multi-soliton was based on separating the solitons far apart. But yes, these solitons, they also decay. They have exponential decaying tails. So how do you know you don't get tiny, exponentially small imaginary parts in the energy or momentum, or whatever physical quantity you want to calculate?
No, we can show that asymptotically, the N-Soliton factors into separate N1-soliton solutions.
Yes.
So this is what we can show. For the one-solitons, we can use PT symmetry to establish PT symmetry. But despite the fact that we may deform them, I can use two arguments. For the one-soliton, I have two options. I can absorb a shift in the integration limits, or I can use the fact that it's conserved, and I can use it in T. Yes. So therefore, for two-soliton, I can still use this because I have T and X.
Yes.
So I can use it simultaneously. For N-Solitons, I need something else. There's no guarantee.
No,
and we use the fact they separate.
I understood the general argument.
Okay.
I was just worried about exponential tails that might remain after you separate them.
Yeah, I don't think so. Or is your question about stability? Yeah?
No. Just about reality. Just about reality of energy, momentum, etc. So I thought, I mean, it must be possible to look at the imaginary part of E and momentum, whatever. They are defined by some integral over a density. So if you can show that the density for the imaginary part of the physical quantity, whatever it is a complete derivative, then you probably can kill it by looking at the boundary values, no? At infinity.
Yeah, you could. Or if it's an odd function, you see, here's the plot. Yeah.
Yes.
So this is what it is, right? So that's what happens for the one soliton, because I can move it just to 0 if you like, and then it's just an odd function and nothing is left over. Yeah. So you worry about little remnants here, which spoil the structure, right?
Yes.
I don't think there's any left. Yeah.
Okay. Okay, thank you. And if I can ask more questions after the end of the second, after the last talk, if the Zoom is still there and Andreas is willing to bear with me, then I will ask then. Thank you so much.
Yeah, I have a naive question.
But sorry, okay, can you also maybe ask after the session? Otherwise, we will be delayed.
Yeah, it's okay. Yeah, okay.
But otherwise, write you also in the chat, and we'll keep track of all questions.
Yeah, okay.
Okay.
Thank you very much, Andreas, for your talk.
Thank you.